One application is related to ecology, and here we suppose that I have f of t, and this denotes the number of individuals in a population at time t. So earlier we said that f of t denotes the stock of some quantity at time t, and now we are going to think of that quantity as the number of individuals in a population. Now that population can be anything. That population can be a particular colony of bacteria. The population can be the polar bears in the Arctic. The population can be anything. And we are concerned about f of t, and f of t is the number of individuals in a population at time t. As I said, the population could be a particular colony of bacteria. The population could be the polar bears in the Arctic. The population could be anything. So here, if I consider f prime t by f of t, if I consider this, in this case, so I know what f prime t by f of t is. It is the relative rate of increase of the stock at time t. It is the proportional rate of increase of the stock at time t. But now in this case, I know f of t denotes the number of individuals in a population at time t. That means this is the relative rate of increase of the number of individuals in a population, and obviously at time t. But now let's call this, if I'm concerned about the relative rate of increase of the number of individuals in a population at time t, I can call this the per capita rate of increase of the population at time t. And in this case, so f prime t by f of t is the per capita rate of increase of the population at time t. Now, if there is no immigration, there is no emigration, that means people are not going out, people are not coming in. And when I say people, I'm also concerned about any individual. So if I'm concerned about a particular colony of bacteria, there is no immigration and there is no emigration. And even if I'm thinking of the polar bears of the Arctic, obviously I'm concerned about no immigration and no emigration, and that means individuals are not coming in and individuals are also not going out. So if that is the case, then the per capita rate of increase of the population would be equal to the difference between the per capita birth rate and the per capita death rate, because we are not concerned about individuals moving in and out of the population. Now, per capita birth rate and per capita death rate are going to depend on many factors, which I'm not concerned about here. But those factors can be food supply, those factors can be age distribution, those factors can be disease, those factors can be living space for the population. There can be many factors which influence per capita birth rate and per capita death rate, and the difference between per capita birth rate and per capita death rate is going to influence the per capita rate of increase of the population at time t. It is going to influence this f prime t by f of t. This is the case if there are no individuals going out of this population, that is, there is no emigration, and there are no individuals coming into this population, that is, there is no immigration. So keeping that in mind, if I think of, let me get back to this. If I think of this f prime t, let me write this here, f prime t is equal to r f of t, and we know this is the case for all t. if and only if f of t is equal to ae raised to the power rt for a constant a. This is exactly what I had written earlier. Now, if I consider this equation, this reflects a very simple model of population increase, that the per capita rate of increase of the population is a constant. The per capita rate of increase of the population is f prime t by f of t, and it is a constant r. And if this is the case, if we have a constant relative rate of increase of the population, if we have a constant per capita rate of increase of the population, if that is the case, if f prime t divided by f of t is a constant r, this actually implies this, and that means the population, so f of t is nothing but the number of individuals in the population at time t, and that just means the population is growing exponentially, because that is equal to a e raised to the power rt. So there is an exponential growth of the population. The point to note here is that with what is given in this setup, I know that if there is a constant relative rate of increase of the population, if there is a constant per capita rate of increase of the population, which is r, if there is a constant f prime t by f of t, I know that is a constant r. If that is the case, that just means that the population is growing exponentially. Now, in reality, that is not going to go on for forever. That is not going to go on forever. The fact that population, it's not the case that population will always keep on growing exponentially, in the sense that if there is an exponential growth, it will be, but it will be only for a limited period of time. So the point to note here is that in reality, the population will not grow exponentially forever. It will, or in other words, I can write the exponential growth can go on only for a limited time. And if this is the case, that means if I say that the exponential growth can go on only for a limited time, and in reality it's not the case that population will grow exponentially forever. The exponential growth can only go on for a limited period of time. Now that means I cannot assume that this is the case, because if this is the case, that means population is growing exponentially. The point to note here is that we cannot then assume that the relative rate of increase is constant. That means we cannot assume that the per capita rate of increase of the population is constant, because if that is the case, that means population is growing exponentially. And in fact, what we have to assume here is that population may go on growing exponentially approximately for a limited period of time, but after some time has passed, or in other words, after population has reached a certain quantity, then the per capita rate of increase is not going to go on. In fact, the per capita rate of increase will turn negative. The point to understand here is that we have something called K, which is the population's carrying capacity. What I mean by K, or the population's carrying capacity, is that this is what we are capable of carrying. This is what the environment is capable of carrying that population. So that's the carrying capacity, in the sense that population may grow exponentially till the time we reach K. After this point, the per capita rate of increase will actually turn negative. And this is something which is understandable, because it's not the case that any population can keep on growing. There will be a time after which, when that population has reached its carrying capacity, that means the environment can no longer hold that population. After that, the population will actually start to decline. And what that means is that the per capita rate of increase of that population will turn negative. This is precisely because of the environmental factors in place, that we take up any population whatsoever, that population will grow until it reaches its carrying capacity, until it reaches the point wherein and after that point, the environment is not able to hold that population. So in this case, the point to note here is that we cannot assume that the relative rate of increase of the population, or the per capita rate of increase of the population, is constant. Because if we assume that f prime t by f of t is r, that just means that the population is growing exponentially, and that is certainly not the case. The fact is, we have to assume that population is growing approximately in an exponential manner up till quantity k, which is called the population's carrying capacity. After that point, above that quantity k, the per capita rate of increase of the population in fact turns negative. That means after that point is reached, the environment is no longer able to hold that population. So in this case, we can write that we cannot assume that the relative rate of increase is constant. Instead, we assume that once the population is above k, and we know what k is, the per capita rate of increase turns negative. And that means we can say till k, the population grows exponentially in an approximate sense. Now, what we have now assumed, I think, what we have assumed here is, and it can be actually expressed by this equation, that we have f prime t is equal to r f of t one minus f of t by k. Now here we can see that if f of t is small in proportion to k, that means the population is well below its carrying capacity. That means this So if f of t is quite small in proportion to k, and that means the population is well below its carrying capacity, that means this fraction is going to be really very small. Okay, and that means I can say that f prime t will be approximately equal to r f of t. So that means I can say that the population is increasing exponentially in an approximate sense. So here I can say, so this is when f of t is quite small in proportion to k. And that means f of t by k is very small, so I can write this. And if I write this, that just means that f of t increases exponentially. But this is when f of t is small in proportion to k. If that is not the case, if f of t becomes larger and larger, this f of t by k, this fraction is no longer then small. Okay, and if it is not small, that means this factor becomes important. 1 minus f of t by k, this whole thing, this becomes important. As f of t gets larger, f of t by k, this fraction assumes greater significance, and in fact that means I can say that this 1 minus f of t by k, this factor then assumes greater significance. So then I cannot say that f prime t is approximately equal to r f of t. Then I cannot say that the population is increasing exponentially in an approximate sense. This is when f of t becomes larger. So if f of t becomes larger, that just means that f of t by k, you cannot say that this fraction is small. And if that is not the case, that means 1 minus f of t by k is something. It is definitely not approximately equal to 1. So in this case, we can say that f of t, or let me write as f of t becomes larger, I can then say that this factor 1 minus f of t by k, this assumes significance. And this implies we cannot say that population is increasing exponentially in an approximate sense. And in fact, if this is the case, if f prime t is equal to r f of t, 1 minus f of t by k, if this is the case, and f of t is not equal to 0, and also this, so if you have this and this, then f of t must have this form. Then f of t will be equal to k by 1 plus a e raised to the power minus rt, again for some constant a. Keep in mind the fact that k is the population's carrying capacity for some constant Now let's say, as I said, f of t is not equal to 0. The number f of t denotes the number of individuals in the population at time t. It's never the case that it's just 0. So if we assume that f of t is not identically equal to 0, and I also take into account the fact that population grows exponentially in an approximate sense till the time we reach k, after that the per capita rate of increase turns negative. Keeping that in mind, so if I know that f prime t is equal to r f of t multiplied by 1 minus f of t by k, and I know that f of t is not equal to 0, then I can say that f of t has to have this form, must have this form. Which form? F of t should be equal to k divided by 1 plus a e raised to the power minus rt. Keep in mind the fact that k is the population's carrying capacity, a is a constant. Now let's say we are at time t is equal to 0, and at t is equal to 0 we have n naught individuals in the population. N naught individuals in the population at time t. That means f of 0 is equal to n naught. I know f of t is equal to k upon 1 plus a e raised to the power minus rt. Here if I put f of 0, that means I have, and obviously just keep this in mind that that r is greater than 0. So if t is equal to 0, I know that f of 0 is equal to, in this case f of 0 is equal to k by 1 plus a, because then it will be e raised to the power 0, which will be 1. And that means I can now write n naught is equal to k by 1 plus a, and that means I can write n naught plus n naught a is equal to k, and that just means in this case I can write n naught a is equal to k minus n naught, and I can then write a is equal to k minus n naught by n naught. So let's say n naught is less than k. When we start out at t is equal to 0, the population is certainly much below its carrying capacity, so n naught is less than k. If that is the case, if n naught is less than k, and that makes sense, we can see that this is going to be greater than 0. If n naught is less than k, obviously that means n naught I know is greater than 0. N naught is less than k, so here both numerator and denominator are greater than 0. That means a is greater than 0. So if a is greater than 0, so that means a is greater than 0 in this case. Also, if you take a look at f of t, which is equal to k by 1 plus a e raised to the power minus rt. Now in this case, I know that a is greater than 0 from what I have just got. Alright, and now I can say that if I just start to differentiate this with respect to t, I see that f prime t, it will turn out to be greater than 0. And if it is greater than 0, that means f of t is strictly increasing. That means as time increases, the population, the stock of individuals, or the number of individuals in the population, that number increases. So f prime t, so f of t can be written as it can be written as k 1 plus a e minus rt raised to the power minus 1. So f prime t can be written as f prime t can be written as minus k 1 plus ae minus rt raised to the power minus 2 ae raised to the power minus rt and then I should write minus r. And we can see from here that this is nothing but that means I can write f prime t is equal to rk a e raised to the power minus rt divided by 1 plus ae raised to the power minus rt squared. And I can see from this that this is greater than 0. I know r is greater than 0. I know k is greater than 0. I know that e raised to the power minus rt is greater than 0. Whatever is there in the denominator, I know that is greater than 0. I have just now established that a is greater than 0. That means f prime t is greater than 0. And if f prime t is greater than 0, this implies f of t is strictly increasing. And if f of t is strictly increasing, also if you just take a look at what f of t is, let me write that again, k upon 1 plus ae raised to the power minus rt. Here you can see that as t tends to infinity, that means you go on and on and on. As t tends to infinity, this expression tends to 0. ae raised to the power minus rt, because this expression is nothing but a upon e raised to the power minus rt. If t tends to infinity, that means this tends to infinity, a is greater than 0, so this expression tends to 0. So ae raised to the power minus rt tends to 0. That means the denominator tends to 1. And that just means that f of t tends to k. Keep in mind the fact that we are obviously assuming r is greater than 0. So I think this establishes what we started out, that as we go on, the population reaches its carrying capacity. It reaches a point. After that point, the per capita rate of increase that turns negative. Because you can also see from here that if I see this, or let me write it again, f prime t is equal to r f of t 1 minus f of t by k. If f of t is more than k, that means f of t by k is greater than 1. And if that is the case, this expression will be less than 0. And if that is the case, that means f prime t by f of t is equal to r and then something negative multiplied by something negative. And r I know is positive, so this is the per capita rate of increase, which is going to turn negative then. And that's exactly what I started out with, that once we reach the carrying capacity, after that point, if the population is above that quantity, the per capita rate of increase turns negative. We also have to keep in mind that the way we have formulated our expression here, f of t, as I said, if if this is the case, if f prime t is equal to r f of t multiplied by 1 minus f of t by k, if this is the case, that means f of t has to have this form, and that just implies that as t tends to infinity, the population reaches its carrying capacity. F of t tends to k. Now, if we denote the function in this manner, this function is actually called a logistic function. It's given a special name. It's called a logistic function. And if we have to denote this graphically, we can see this, that this k is the carrying capacity, and we know that as t tends to infinity, so that's what we see, as t tends to infinity, f of t is, we can see that f of t is going to tend to k. We can also see that it's a strictly increasing function. F prime t is greater than 0, so it's a strictly increasing function. Also, we see that as t tends to infinity, f of t tends to k. K is nothing but the population's carrying capacity. So that was one application of this concept of a constant relative rate of increase, and the fact that this is the case if and only if that stock is growing in an exponential manner. This is if and only if the case if the function has that function is of the type a e raised to the power minus rt. So this is one application which is a very important application related to ecology with respect to the constant relative rate of increase, and the fact that that is possible if and only if the population is growing exponentially.